42 miles per hour. That's it.
A light breeze. A joke.
And yet 2,800 feet of steel just let go.
$6.4 million. Gone in an hour.
It didn't fall. It danced.
It didn't dance, Mark. It convulsed.
Steel girders twisting 45 degrees, like licorice.
Engineers called it state-of-the-art.
Physics called it a tuning fork.
The insurance companies called it a total write-off.
You see the footage? It's hypnotic.
It's nauseating. That's tax money rippling like water.
Concrete shouldn't ripple.
And bridges shouldn't earn nicknames.
Galloping Gertie.
Sounds cute.
Felt like a death trap.
Drivers actually aimed for the center line to avoid falling off.
Because the sides were swinging 28 feet up and down.
28 feet. Imagine the motion sickness.
Imagine the G-force hitting the bolts.
Imagine the arrogance of the designer.
Leon Moisseiff, the golden boy.
He wanted it slender.
He made it an airplane wing.
He forgot bridges aren't supposed to fly.
It generated Lift Elena.
It generated a lawsuit.
November 7, 1940.
The day the math stopped working.
The wind hit the plate girders.
Solid walls. Nowhere for the air to go.
So the bridge took the energy.
And the bridge pushed back.
And the bridge pushed back.
Fancy word for we screwed up.
It's a self-feeding loop.
Like bad debt.
Like bad debt.
Wind pushes harder, bridge twists harder.
Until the steel hits the yield point.
Snap, divide, distre, monument, boh. Mine. One cable goes, then the vertical suspenders, like a zipper, opening up hell.
The sound must have been deafening.
Screeching metal, exploding rivets.
Screeching metal, exploding rivets.
And one car stuck in the middle.
Leonard Coatsworth's sedan.
He crawled out on his hands and knees.
Blood on his hands. Concrete tearing his pants.
But he left something behind.
But he left something behind.
Tubby, the Cocker Spaniel.
The only casualty.
Paralyzed with fear in the back seat.
Mark this. A professor tried to save him.
Professor Farquharson, a wind expert.
The irony is heavy.
He walked out onto the twisting deck.
The bridge is bucking like a rodeo bull.
He reaches the car.
The dog bites him.
Panic. Pure instinct.
The professor retreats.
The dog rides the car down.
190 feet.
Into the freezing Puget Sound.
A $6 million coffin for a dog.
And a tombstone for Moisseiff's career.
It changed everything.
It embarrassed everyone.
Before this, they just worried about gravity.
Will it hold the cars?
Heavy loads, static forces.
Boring. Predictable.
They ignored the air.
They ignored the invisible.
They built a sail, anchored it to the ground, and were shocked when it caught the wind.
Deflection theory, they called it.
Cheaper theory is what it was.
Lighter materials, less steel.
Higher profit margins.
You know it.
The Bronx Whitestone Bridge, same design.
It started shaking too.
They had to rush out and bolt trusses to it.
Panic retrofit.
But Tacoma, too late.
It was doomed from the blueprint.
The aspect ratio was 1 to 72.
Too thin.
A ruler on its edge.
Wobbly, unstable.
You push a ruler, it bends.
You push this bridge, it breaks.
And the oscillations.
36 cycles per minute.
That's a heartbeat.
The bridge was alive, Mark.
And then it died.
Violently.
The center span dropped first.
Ripping the side spans upward.
The towers bent back like bows.
12 feet of deflection toward the shore.
Steel plates buckling.
Bolts shearing off like bullets.
The splash was massive.
The silence after was worse.
Just the wind.
And the shame.
It wasn't a storm.
It wasn't a hurricane.
It was a Tuesday morning breeze.
That's the scary part.
Nature didn't even try hard.
She just tapped it.
She just tapped it.
We build monuments to our ego.
Physics tears them down.
Every time.
Every time.
Are we done gawking at the disaster?
Not yet. We need to dissect the corpse.
The money trail.
The physics trail.
The human error.
The aerodynamic suicide.
Fine. Let's open the file.
The engineering marvel that couldn't stand still.
Let's see what made Gertie gallop.
And why she had to die. Let's strip the romance away and look at the skeleton of this disaster. The Tacoma Narrows wasn't killed by a monster storm. It was killed by a fundamental misunderstanding of fluid dynamics that borders on criminal negligence. In 1940, civil engineering was obsessed with one thing: gravity, vertical loads. If you could hold up the cars and the steel, you were a genius. They treated the wind like a static force, just a gentle push on the side of the bridge. They calculated for a steady pressure of 30 pounds per square foot, which sounds robust on paper. But wind isn't a static hand pushing against a wall. Wind is a fluid. It's chaotic, it has viscosity, and when it hits a solid object, it doesn't just stop, it curls, it accelerates, and it creates low-pressure zones. Leon Moisseiff designed the bridge with solid plate girders, 8-foot-tall sheets of solid steel running the entire length of the sides.
And he did it because it was cheaper. Mark, let's not pretend this was purely an aesthetic choice. Plate girders are significantly less expensive than open trusses. The PWA, Public Works Administration, put up a grant for nearly $3 million, but they were watching every cent. Moisseiff came in with a design that was lighter, sleeker, and most importantly, cheaper than the competition. He stripped the bridge down to its absolute minimums. The deck was only 39 feet wide for a span of 2,800 feet. That is an insanely narrow ratio. He was selling them a ribbon of steel, a marvel of modern economy. He promised them a bridge that looked like the future, but he sold them a structure that had the aerodynamic stability of a leaf in a hurricane. It was vanity pricing. He saved money on steel, sure, but he bought a $6 million catastrophe.
The physics of the collapse is actually terrifyingly simple once you look at the cross-section. Because of those solid plate girders, the cross-section of the bridge was essentially an H shape. When the wind hit that solid wall of steel, it couldn't pass through like it would in an open truss. It had to go over and under. This created what we call flow separation. Vortexes, swirling pockets of low pressure, began to shed off the top and bottom edges of the girder. This is the von Karman vortex street effect. These vortexes didn't shed randomly, they shed rhythmically. One sheds from the top, pulling the bridge up, then one sheds from the bottom, pulling the bridge down, up, down, up, down. The wind was literally pumping energy into the bridge structure, timed perfectly with the bridge's own natural frequency.
And the warning signs were there from day one. This isn't a case of nobody knew. The workers building the deck were getting seasick. They were chewing on lemons to keep their lunch down while pouring concrete. They nicknamed it Galloping Gertie months before it opened. The bridge was moving in vertical waves of up to 5 feet even in light winds. And what was the response from the brilliant minds in charge? They installed hydraulic buffers that snapped instantly. They tied it down with cables that snapped like thread. They knew. The toll plaza operators knew. They sometimes saw cars disappear into the troughs of the waves while driving across. Yet they kept the bridge open. They kept collecting the tolls. They let the public drive on a structure that was clearly behaving like a living animal. That is the definition of corporate arrogance. They assumed that because it was made of steel, it wouldn't break. They bet human lives on the assumption that motion didn't mean failure.
The real death sentence came at roughly 10 a.m. on the day of the collapse. Before that moment, the bridge was galloping, moving up and down in a sine wave. That's bad, but it's survivable. But then something changed. A cable slipped in a mid-span band, or perhaps a gust hit at just the right angle, and the motion shifted from vertical to torsional. The bridge started twisting. This is where the physics gets violent. Once the twisting started, the bridge became an airfoil. As the left side went up, the angle of attack increased, catching more wind, which pushed it up even harder. As the right side went down, the wind pushed it down further. It was a positive feedback loop. Aerodynamic instability. The bridge was extracting energy from the wind and using it to destroy itself. It wasn't resisting the wind anymore. It was feeding off it. The angular rotation hit 45 degrees. The acceleration at the edge of the deck exceeded gravitational pull, meaning if you were standing there, you would have been thrown into the sky, not dropped. Steel isn't rubber, Elena. It has a yield point, and at 11 a.m. physics collected its debt.
It's interesting you mentioned debt, Mark, because the financial fallout was a mess of epic proportions. The state of Washington had a policy covering the bridge for $6 million. But here's the kicker, the ultimate punchline of corruption. The insurance agent, Hallett R. French, had pocketed the premiums for one of the largest policies. He never filed the paperwork. He bet that the bridge wouldn't fall down, and he lost. He was sitting on the premiums, thinking he had free money, and then he watched the newsreel of the bridge splashing into the Puget Sound. He went to prison for grand larceny. That is the perfect microcosm of this entire project. Corners cut, money stolen, risks ignored, all wrapped up in a shiny, modern package that collapsed the moment reality applied. A little bit of pressure.
The carcass of the Tacoma Narrows Bridge lay at the bottom of the Puget Sound, a twisted monument to human ignorance. But the real casualty wasn't the steel. It was the deflection theory. Before November 7, 1940, engineers like Moiseau believed that if you made a bridge long enough and heavy enough, gravity would naturally stabilize it. They thought mass was the answer to everything. The collapse proved that gravity is just one player on the field. And frankly, it's the lazy one. Gravity pulls down. Simple. But wind pulls up, twists, pushes, and sucks. The investigation board, the Carmody Committee, didn't mince words. They explicitly stated that while the bridge was strong, enough to hold the cars, it was aerodynamically incompetent. It was a structural suicide note written in steel. This forced a shotgun wedding between two disciplines that had never spoken before: civil engineering and aeronautics. Suddenly, bridge builders had to start thinking like airplane designers.
And that marriage was expensive. Mark, the immediate fallout was a total freeze on similar projects. The Bronx-Whitestone Bridge in New York. They panicked. They rushed in and installed massive stiffening trusses, basically ugly metal corsets, to stop it from moving. That cost millions. The Deer Isle Bridge in Maine, same thing. Moiseau's reputation was incinerated. He died 3 years later of a heart attack. Some say it was stress. I say it was the crushing weight of knowing his masterpiece was a lethal joke. The insurance industry changed overnight. No more handshake deals or pocketed premiums. If you wanted to insure a suspension bridge after 1940, you needed wind tunnel data. You needed proof that your design wouldn't flutter away in a breeze. The cost of infrastructure didn't just go up because of materials, it went up because we finally had to pay for the insurance of aerodynamic testing.
Let's talk about the replacement. They didn't just patch it up, they obliterated the old design philosophy. The new bridge, opened in 1950, earned the nickname Sturdy Gertie. Why? Because where the old bridge had those solid, wind-catching 8-foot plate girders, the new one had open trusses that were 33 feet deep. Think about that difference, 8 feet of solid wall versus 33 feet of open lattice. It wasn't a wall anymore, it was a sieve. The wind could pass through the structure rather than fighting against it. They added damping mechanisms, they added slots in the deck, literal holes in the road, to equalize pressure above and below. They stopped fighting the wind and started negotiating with it. This is the difference between arrogance and engineering. Arrogance builds a wall. Engineering builds a grate.
And that negotiation continues today. Look at the Yavuz Sultan Selim Bridge in Turkey. It's a hybrid. Suspension and cable stayed. It's massive, wide, and incredibly stiff. But before they poured a single cubic meter of concrete, they spent months in wind tunnels testing scale models against every possible vortex scenario. They tested for flutter, for buffeting, for galloping. That testing phase alone cost more than the entire original Tacoma Narrows budget. But that's the price of safety. We learned that cheap is actually the most expensive option on the table because cheap ends up at the bottom of a river. The legacy of Tacoma Narrows isn't the collapse, it's the check we write today to ensure it doesn't happen again.
It redefined the safety factor. We used to calculate for maximum probable load. Now, we calculate for maximum credible failure. We assume the wind will try to kill the structure. We assume the resonance frequency will try to tear it apart. When you drive across a modern suspension bridge, you aren't just driving on asphalt. You are driving on a century of lessons learned from failure. You are driving on the ghost of Galloping Gertie. The physics didn't change in 1940. The wind didn't get stronger. We just finally stopped ignoring the invisible forces.
And we stopped trusting genius designers implicitly. No more golden boys. Now, it's peer review, wind tunnels, and redundant systems. We traded the sleek, artistic lines of Moisseiff's vision for the bulky, safe reality of truss systems. It's not as pretty. Maybe it doesn't look like a ribbon floating in the sky.
No, it looks like a cage.
But it stays up.
Exactly. A bridge that falls is just a very expensive dam. A bridge that stands is ugly, expensive, and absolutely necessary.
So the verdict.
The verdict is that nature doesn't care about your budget, your timeline, or your aesthetic vision. If you build a sail, nature will blow it over. If you build a wing, nature will make it fly.
And if you want it to stay put,
you better pay the wind its tax.
in steel or in cash.
Preferably both.
Case closed.
Case closed.